All right, let's do this. This is part 2 of the rotational inertia video. So if you go to page 27, you're going to see pretty much the different shapes, and you're going to see their moment of inertia, right? Or rotational mass, or rotational inertia, whatever you want to call it. All right, so let's do some problems. Okay. And I think here it says to explain the relationship between the period and the length of a pendulum using rotational inertia. I think I talked about that in the previous video. Okay, so now we're going to do this RT11 here. Okay. Each of the 10-point masses in each case is identical. The solid lines in each figure represent an axis about which the masses are going to be rotated. Okay. So it says rank these arrangements on how hard it will be to start the system rotating. So this has to do with rotational inertia. So the higher the rotational inertia, the harder it is to rotate the object. So the axes are darkened. So here, I'm going to look at each one of these distances as a 1, basically, just a unit of 1. And I'm going to look at each one of these masses as, should we just make it 1? Should we just make it m, whatever. So we can make each one of these masses 1 unit of mass. All right. So for the first 3, okay, it's just going to be, so basically we're going to compare m r squares, because the sum of the mr squares, the moment of inertia of a single mass away from an axis of rotation is just going to be mr squared, and you just add up all of them and you can compare. So in the first case, you're going to have 3 masses, right? And I think we can just put a 1 here and a 1 here square. So each m and each r is 1. So for the first line here, we should have a 3. For the next line, we should have 1 times 2 square, so it's 3 times 2 square. Right? And for the last one, you have 1 mass, but it's 3 units of distance away, so that's going to be 3 square. And you just take this and add them up. So that's 9, 12, and how much is that? 12 and 12, so 24. Okay? And you would do the same thing for all of them. So it doesn't matter whether the mass is on the right or the left. You would just take those moment of inertias, add them up, and this is what you're going to get. So you're going to get 24 for the first one. You should get 13 for the next one. You should get 37 for C, and you should get 16 for D. So the greater the moment of inertia, the harder it is to get it to start rotating. So it's going to be C, then A, and then D and B. Okay, and the explanation is basically what I just said verbally now. Okay. Okay, number 38. A hoop has a diameter of 0.2 meters and its mass is 0.4. What is the rotational inertia? So this is pretty simple, actually. I equals, for a hoop, it's the moment of inertia is mr squared. So you just do 0.4 times 0.2 square, and you get an answer there. Okay, and the units are kilograms times meters square. Kilograms, meters square. A half a kilogram soccer ball has 25 centimeters circumference, so you got to pay attention to the units. So the circumference is 2 pi r is 25 centimeters, which is 0.25. So the radius here is going to be I didn't do the math, but it's 0.25 divided by 2 pi, basically. Make sure you put the 2 pi in parentheses when you divide in, when you're using the calculator. So basically, to find the moment of inertia. Now, a soccer ball is a sphere. So the moment of inertia for that is 2/5 mr squared. So it's 2/5 the mass, which is half, times 0.25 divided by 2 pi. You square the whole thing. A construction crew has to move some solid log poles to the end of the parking lot. The logs are 3 meters long, have a diameter of 20 centimeters, and a mass of 10 kilograms each. One crew flips the logs end over end, and the other crew rolls the logs along, who has an easier time moving them? So we have to figure out basically the moment of inertia of the log when we rotate it in different ways. So some people do this. So if this is the log, some people are just going to roll it, and some people are going to do this. They're going to lift it here and drop it. Lift it and drop it. So you can probably see that the ones that are lifting it and dropping it are going to have a harder time. Now the moment of inertia of that, of something like this is the axis of rotation, right? Or actually, if we go following what I did earlier, this is the axis of rotation. So you're going to lift from here and drop. So this is like a mirror stick that you're going to rotate around one of its ends. So if you look at higher, you're going to find that it's 1/3 ml square. So it's 1/3. The mass is 10 kilograms, and the length is 3 square. So that should be 30 kilograms meters square. Now, if you roll them, it's a cylinder, so it's 1/2 mr square. So it's 1/2 times 10. Now the diameter is 20, so which means radius is 10 centimeters, so it's 0.1 meters square. Now if you do the math here, I think you get 5. Do we? You get 0.05. Okay, kilograms meters square. So rolling is going to be easier. Now this problem here I did in part 1 of the video, but I do it quickly again. This is just like the RT11 I talked about earlier. So in here, let me just make sure I'm still recording, because sometimes this thing misbehaves. Okay. Okay, so here, if the axis of rotation is here, you're going to do 5 times 2 square plus 7 times 2 square, and you get a moment of inertia. Here, the axis of rotation is at the end here. So you do 5 times 0.5 square plus 7 times 4 square. And the one that's going to have a higher moment of inertia is going to be harder to spin. All right. All right, several objects roll without slipping down an incline, vertical height h. So we're going to roll these objects down the ramp, and we're going to figure out which one is going to get down there first. So this is what we have. We have a hoop that has a moment of inertia with a coefficient of 1 in front of the mr square. We have a marble, which is a sphere. That's 2/5. Okay. We have a cylinder, which is half. We have an empty can, and then we'll talk about what the coefficient of that should be. And we have an unopened can. And then we have a box. Now the box is not going to roll, so this is going to definitely win. Okay, so it's not going to waste any of its energy to rotation. The empty can is basically can like this, so it's open, but it's also closed at the bottom here. So that's going to be a little faster than a hoop, because some of the mass is kind of like distributed closer to the axis of rotation. I will try this in class actually. We'll run all this down a ramp, and we'll see which one wins. So this has some mass in here. So that should be a little bit less than 1. Okay, not much, but definitely better than 1. An unopened soup can, so there's always liquid in there. So when it starts to roll, the liquid will go to the outside. So it's kind of like it's going away from a cylinder and it's getting closer to a hoop. But not a lot of the liquid goes to the outside. So maybe just enough so that it's greater than, that it's greater than half. Okay? So the mass is distributed kind of like further away from the axis of rotation. So the ones that are going to win is the one that's going to win is definitely the one with the smallest number. So I think it's going to be the sphere in position number 2 after the box. Then comes the cylinder. Then comes this unopened can. Then this comes the empty can, and the hoop comes in last place. So that's the order. All right, let's look at this RT12 here. So we're going to try to rank the moment of inertia. So here we're going to try to figure out which one has the mass distributed the furthest away from the axis of rotation. So if I draw a circle here, if I inscribe a circle inside here that has a radius r, I can see some of the mass is in those corners there. Okay, so the mass is distributed further away than if you're looking at the ring. Okay, so this one is going to have a greater moment of inertia. Then comes the ring, because all the mass is distributed around this circle. And then for the disk, the mass is distributed throughout the disk. So that should be a B. Okay, number 13. Will the moment of inertia of the rod be greater about the left hand? So in other words, if you put your axis of rotation here, is it going to be easier to rotate this if you put your hand here? Or is it going to be easier if you put your hand here? Well, if you put your hand on the left, the 3m is further away. So that's a heavy mass, and it's the furthest away from the axis of rotation. If you put your hand on the right here, the m is the one that's furthest away. So the position of 2m is the same for both cases. So in this case here, it's going to be harder to rotate this object here when you put your hand on the left side. So the answer should be greater about the left. All right, let's look at RT14. So for this one, rank the difficulty of holding the meter stick. So this is going to go back to torques. So the one that's going to generate the most torque is going to be the one that's going to be the hardest to hold, basically. All right, so the torque by this, I'm going to do this differently than what you have in the answer key. I'm going to extend the line of force here, which is mg, by the way, for all of them. So I think we just have to compare how far is the line of force from the axis of rotation, which is at your hand. Right? So we just have to figure out what these distances are, because the mg is the same. So that distance, if I call this L, that distance is just going to be L cosine of 30. This is just going to be L over 2. This is just going to be, if I extend this line here, I'm looking at that segment, which is basically the same as this segment. So it's going to be L sine of 60. Here, we're looking for this segment here. So that's L cosine of 45, which is the same as sine of 45. And this one is just going to be L. So cosine of 30 is radical 3 over 2. Sine of 60 is also radical 3 over 2. And cosine of 45 is radical 2 over 2. So the order should be E in first place, or is the hardest to it's the hardest to hold. And then comes A and C, it looks like, tied for the next place. And then we have D, and then B. Yep, okay. Let's look at the last one here, RT15. So now basically here we have to figure out which one of these guys creates more torque. Is it case A or B? So for case A, this is 5 newtons. So it's 5 and L over 2 away from your hand, plus this is going to give you 10 newtons. That's 1 kilogram, and distance L. This one is going to be 10 L over 2 plus 5 times L. So it looks like the left side is greater. So it should be the torque that the student has to provide has to be greater in case A. And you actually don't even have to do the math. You can see that in case A, the 1,000 grams is further away, right, than in case B. So the further the mass, the more the torque.